This is lesson 9 of the chemical bonding storyline. The chemical bonding storyline is titled, Why Do Some Things Get Colder or Hotter When They React? I've chronicled the first half of the chemical bonding storyline, which encompasses 7 lessons that nicely thread into one another. We've now reached the second half of this bonding storyline. Lesson 8 deals with the exothermic reaction involving alkali metals in water. Lesson 9 is a big chunk. Are you ready for it? After the reaction of alkali metals in water, which is clearly exothermic, I will now connect that lesson 8 to lesson 9, where students will be modeling the making of chemical bonds, learning about kinetic versus potential energy. Students will then connect the making and breaking of chemical bonds through drawing models, followed by a simulation that lets them further manipulate this phenomenon. Lesson 9 is centered around the following question: why do some reactions warm things up? This lesson took quite a bit of time, a total of 4 class periods. At my school, each period is roughly 50 minutes per lesson, and I taught this lesson during the 3rd quarter of the academic year. In order for students to be able to answer the central question around which lesson 9 is focused, why do some reactions warm things up? We're going to ask them the following: how to model the making of chemical bonds. What you're seeing here are the components that students can use to make this happen. Now remember, lesson 5 is when students were actually modeling the breaking of chemical bonds, as you can see in this GIF animation. And this visual certainly helped them to figure out how best to model the making of chemical bonds. Here you're actually seeing my 2 students placing a small magnet underneath the ramp, starting the speedometer, and as a result of releasing a metallic marble, which is then connecting to the magnet underneath, the non-metallic marble, albeit slowly, at a speed of roughly 0.09 meters per second, is leaving the system. In the next GIF animation, my students are using 2 much larger magnets, and as a result of that, the marble speed is now 0.48 meters per second. And this data in table form nicely shows you that by using only 1 small magnet, the non-metallic marble leaves the system at a relatively low speed, in this case 0.043 meters per second. Whereas when using 2 much larger magnets, you see that the non-metallic marble leaves the system at a much greater speed, in this case 0.430 meters per second. Let's put this into a bar diagram. In essence, the stronger the magnet, the greater the speed that the non-metallic marble gains as a result of making that bond. You can also show this relationship as the speed of the non-metallic marble as a function of the mass of the magnet. Again, the greater the mass, the greater the speed of the non-metallic marble leaving the system. So now that the students modeled and graphed their data for making chemical bonds, how to now connect the breaking of chemical bonds to the making of chemical bonds, just like what happens during a chemical reaction. Therefore, the 2 GIF animations are here shown side by side. But are chemical reactions a result of first the making and then the breaking? Or should we flip it? Yeah, in order for a chemical reaction to occur, we first have to break existing bonds between atoms and then make bonds between 2 different atom combinations. Follow that line. We are first breaking and then making. This GIF animation really helps to take the students to the next level. We're watching here a skier skiing down the hill, and as a result, there's a change in kinetic and potential energy. Once the skier reached the bottom, work can be done by turning unpacked snow into packed snow. Let's unpack this GIF animation. So we're getting a little bit into physics here. Energy is defined as the capacity to do work. Kinetic energy is a result of the motion of the object in this animation. The further down the hill the skier goes, the greater the kinetic energy because the speed is greater. We can equate kinetic energy with thermal energy associated with temperature, which is the energy that is present when a chemical reaction happens. Potential energy is due to the position, in this case starting at the top of the hill, or the composition, which lowers as the skier approaches the bottom of the hill. Chemical potential energy is associated with the positions of electrons and nuclei, electrons being negatively charged and nuclei containing the protons, which are positively charged. So with this GIF animation in mind, students can then go to the drawing board and see if they can connect their modeling of breaking and making chemical bonds and the kinetic and potential energy terms that they've now been exposed to. And I'm showing you here some great drawings by my students that really showed that they were starting to grasp this concept. I had to laugh when a few students included these bicep drawings into their model. See the resemblance to the ramp and the original GIF animation? And several students were quite clever, bringing in actual magnets that would stick to these magnetic dry erase boards to represent the bonds being broken versus the bonds being formed. My students had a lot of fun drawing all these models, thereby connecting the breaking and making of chemical bonds, and also keeping in mind the kinetic versus potential energy at play. Some students instead chose to do their drawings more in a digital manner using the Google Doc drawing tool, as you can see here. So let's take a quick overview of where we're at within our lesson 9. We completed the modeling of the making of chemical bonds. We covered the potential versus kinetic energy in a system, and then we connected the making and breaking of chemical bonds by drawing the actual model on a whiteboard or in a digital form. That means we've now reached our simulation. So that final question related to lesson 9 is, what if we could manipulate the breaking and making of bonds using a simulation? And I'm showing you here a picture of the NetLogo simulation developed at Northwestern University. Let's dive into it. The lesson ends with 3 investigations that all center around this simulation. Investigation number 1 asks the following question: how does adding bonds into this simulation affect the motion of the particles present in the simulation? Let's check it out. I'm showing you here the setup of the simulation, the variables that we have to put in. The top picture shows you the first magnet, labeled magnet 1, with a strength of 1. The bottom picture shows you again magnet 1 with a strength of 8, as shown by the much thicker arrows pointing towards that magnet. How is that going to affect the speed of the metallic marble coming in? The metallic marble labeled as marble B. We've reached here the NetLogo simulation called Bonds and Chemical Energy. And this should look exactly the way it would look for you when you click on the link. I'm going to first click Setup so that we can actually see what's present. And then I'm going to type in the exact variables that the first setup is calling for. 90, 50, 1, 100, 70, and 0. I'm going to click Setup, and then I'm going to hit Go. You can see how the metallic marble slowly goes towards magnet 1. And clearly it's getting pulled back towards magnet 1 and will oscillate back and forth as a result of that magnetic strength. So a bond is trying to be formed, but because there's little to no traction in this system, there is a wobble. Hence the oscillating speed. So the conclusion of investigation 1 involving this simulation: how does adding bonds affect the motion of the particles? As the strength of the magnet increases, the speed of the metallic marble increases. But notice, because there's no friction in this system, the metallic marble oscillates as shown in these speed diagrams. I'm now going to adjust the settings to match with investigation 2. So 90, 70, 0, 10, 10, 3. Setup. We're going to hit go, and we're going to notice that B ever so slowly is going to get attracted to the second magnet. There's no magnetic force on the first magnet, and thereby is going to pass on its energy to object C. As you can see here in this graph, that energy was transferred. And again, we see that oscillation. So the answer to investigation 2, how does forming a bond affect the speed of particles entering and exiting the system? If we increase the strength of the magnet, then the speed transferred from the metallic marble to the non-metallic marble increases, as shown in the graphs displayed on the right. The top graph shows a lower speed because the magnet had a lower magnetic force. The bottom graph shows a higher speed transferred from the metallic marble B to particle C, as shown by an increased speed. In order to answer this third question, let me explain how we're going to set up the simulation. We have the first magnet, which we are going to set to a magnetic strength of 3. Metallic marble B is positioned directly above that first magnet. The second magnet is turned off. It has no magnetic power. We are going to bring into this system, which you cannot see here, a non-metallic marble called A, particle A. We're going to try a couple of different speeds, 1.8 meters per second for the incoming speed, and we're also going to try, with all the other settings exactly the same, a speed of 2 meters per second. Let's watch what happens. All right, let's put those settings in. 10, and 3, and 100, 70, and 0. Let's hit setup to reflect that. And now we're going to give particle A a speed of 1.8. All right, let's hit setup and go. We are seeing particle A come in. It's kicking particle B off. It's breaking the bond. But wait a second. What's going to happen? Particle B clearly did not have quite enough speed to leave the system. It's getting pulled back in to magnet 1. So it did not receive enough kinetic energy to actually leave the system, so this bond was not consistently broken. Let's try it again, but now with a speed of 2. Set up and go. Particle A is coming back in. Again, that's a non-metallic particle. B is now leaving and is not coming back. This bond was now truly broken. So let's summarize this third investigation. How does breaking bonds affect the speed of particles entering and exiting the system? If particle A only had 1.8 meters per second coming into this system, it was not enough to break consistently the bond between metallic marble B and magnet 1, because metallic marble B came back, as you can see from this speed diagram. However, when particle B had a speed of 2 meters per second, it was enough to transfer its energy to particle B, and although particle B slowed down, it did not return to remake that bond. So the bond now was truly consistently broken in this system. So to summarize that third investigation involving the simulation, How does breaking bonds affect the speed of particles entering and exiting the system? The incoming speed of the non-metallic marble, called particle A in our simulation, needs to be enough to cause the bond between the metallic marble and the magnet to break. So to connect that to the breaking of chemical bonds, one needs to have enough thermal energy for a chemical reaction to occur, enough thermal energy to break the existing chemical bonds. We've come to the conclusion of this lesson 9, a big lesson. Could take probably 4 class periods. We started with the modeling of the making of chemical bonds. Next, we did a mini lesson where we're connecting the terms kinetic energy and potential energy as it relates to this GIF animation to thermal energy and chemical energy. Third, we connected the breaking to the making of chemical bonds by using the GIF animation and constructing drawings on either whiteboards or using a digital drawing tool. Fourth, we brought in a simulation that really allowed us to manipulate the various components of this system. That involved really doing 3 brief investigations that involved manipulating the magnets in this simulation, as well as the metallic and non-metallic particles that are coming in or leaving this simulation. And in order to really answer the question that Lesson 9 posed, we have to then dive into Lesson 10 with the central question, why do some chemical reactions get cold and others get hot? So stay tuned for Lesson 10, where we're trying to bring everything together. The chemical bonding storyline again focuses on the NGSS standards as well as the NYSSLS standards in terms of matter and its interactions, and energy change in components of a system. All the individual lessons are available. Just check out the stunning storyline playlist, and all the videos that explain each individual lessons are there for you to watch. If you wish to have all the resources associated with these chemical bonding storyline lessons or any other resources that I have, check the link in the description below, and in exchange for your email, you will get this Google document with all the lessons and their handouts and associated teacher keys. Thank you very much for watching. Bedankt voor het kijken. Tot ziens and see you in the next video.